Welcome all. This is a presentation on nuclear and radiochemistry. This is the fifth session, and in the previous four sessions we have covered the fundamental aspects of radioactivity, the nature of the particles emitted, the stability of the nucleus, and the factors that control the stability of the nucleus. In today's very interesting session, we will try to ask ourselves, is it possible to convert one nucleus into another? In other words, is it possible to convert one element into another? Now this is a very interesting question, and this question of course has not escaped human attention in the last 1000 or 1500 years. People across the world who were scientifically bent were always after methods of converting baser metals like copper and iron into gold, because the ultimate and the most stable metal those days thought of was gold. And people who indulged in these processes were called alchemists in Arabic. And therefore, this is the origin of modern day chemistry. It is very interesting now that we have come a full circle and we are able to convert one element into another by manipulating the number of protons and neutrons that are present in the nucleus. Now, how do we do it, and how different it is from our regular chemical reactions that we do in our laboratories and industries? This will be the subject matter of today's discussion. The first such successful attempt was made by Rutherford, and what he did was he took a stable isotope of nitrogen, nitrogen 14(7). He sent a very fast moving helium nucleus, which is the alpha particle. So what happens essentially is that the two nuclei, the N14 nucleus and the helium nucleus, come together, they collide. One proton is ejected out and oxygen 17 is formed. So we have successfully converted nitrogen 14, which is a stable isotope of nitrogen, into oxygen 17, which is another isotope of oxygen, also stable. In other words, we have successfully brought about the transmutation of one nucleus into another, or one element into another directly. In this reaction, the electrons outside the nucleus in both nitrogen and oxygen and also helium are not at all involved in the reaction. So this is a direct interaction between one nucleus and another nucleus. Helium, because it's fast moving, is called as a projectile. Helium or alpha particle is not the only projectile that can be used. We can also use a proton, we can use a neutron, deuteron, and even gamma radiations. And we'll be dealing these in detail in the next session. But for the present, let us remember that a stable nucleus can be bombarded by a fast moving projectile. It hits this particular nucleus and it becomes unstable. It throws away some particle and forms another stable nucleus. So this reaction is what is called as a nuclear reaction, because we have brought about reaction between two nuclei. It's also called as transmutation because we have converted one element into another element. How does this conversion happen? For the reaction in question, which was done by Rutherford, the N14(7) nucleus picks up the alpha particle, it captures it and forms a compound nucleus which is highly unstable. 14 plus 4 will make it 18 and 7 plus 2 will make it 9. So therefore the unstable nucleus is fluorine 18(9). This is so unstable that it will immediately disintegrate, giving oxygen 17 and a proton. This is generally the mechanism followed in most cases where the projectile, which is a light particle, will be captured by the nucleus, forming something unstable, and that will break up, forming another stable nucleus. So let us now formally define what are nuclear reactions. In nuclear reactions, a stable nuclei is bombarded by a high energy particle like the alpha particle. This high energy particle is called as the projectile. It is absorbed by the nucleus resulting in a highly unstable nuclide, and this breaks up, forming a new nuclide with the emission of another particle. And therefore the overall result is the conversion of one nucleus into another, and hence the phenomenon is called a nuclear reaction or artificial transmutation of elements. Now it is very pertinent to ask, will there be any energy changes during this reaction? We of course know about chemical reactions. From what we do in the laboratory, we are familiar with exothermic and endothermic reactions. Some reactions give out energy in the form of heat. They are called exothermic. Some other reactions require the supply of energy, and therefore they are called endothermic. What about nuclear reactions? Do they liberate heat or do they accept heat? Or in other words, do they liberate energy or do they accept energy? Now this has been evaluated by looking at the energy that comes out along with the reaction on the right hand side of the product. So when you write a nuclear reaction, on the left hand side you will have the nucleus and the projectile. On the right hand side you must write the product nucleus, the particle emitted, and the energy as Q. So you will write it as plus Q. Now this Q is the amount of energy that is either released or absorbed during a nuclear reaction. A positive Q value implies that energy is released, either as light or heat or in some other form. Such reactions are called exergonic or exergic reactions. If the Q value is negative, it implies that energy is absorbed. Now, in most cases, the Q values are negative, and in only a few cases, the Q values are positive. In other words, in order to bring about nuclear reactions, you need to spend energy, and in only a few cases will the system give you energy. Why this is so is a question that we'll ask. Now, for a nuclear reaction to take place, I have already told you that a projectile has to be sent to hit the nucleus. I am using the word projectile, which implies that the particle that I am sending should have very high kinetic energy. Why it should have very high kinetic energy? Let us assume that an alpha particle is hitting the nitrogen 14 nucleus. When you send an alpha particle is nothing but a nucleus of helium having 2 protons. In other words, it is positive. So you are asking one nucleus to collide with another nucleus. Now this is not easy because both are positive and therefore they will repel one another. And closer the approach, greater the repulsion. So therefore our projectile, which is light, should be given a lot of speed and kinetic energy so that it is able to overcome this repulsive factor, Coulombic repulsion, and collide with the heavy target nucleus. Therefore, we have to supply energy in most cases. And the Q value, or the amount of energy that is supplied or given out, is evaluated by noting the difference in the masses of the product and the reactants. This is very interesting because in ordinary chemical reactions, the sum of the masses of the products and the sum of the masses of the reactants are equal. But in nuclear reactions, there is going to be a mass defect. When you count the total mass of all the products formed and the total mass of all the reactants, including the projectile, they will not be equal. There will be a mismatch. The mass may either decrease or it may increase. Now this difference is called delta M, and when you express delta M in atomic mass units and multiply it with 931.5 mega electron volts, which is the value of energy for 1 AMU, you will get the value of Q. So Q is equal to delta M expressed in AMU into 931.5 mega electron volts. So the Q value tells me about how easily a particular nuclear transmutation can take place. Let us now compare ordinary chemical reactions with nuclear reactions. I have been, of course, doing it indirectly, but let me do it more formally. In chemical reactions, the elements involved retain their identity. The atoms retain their identity. You can even take, for example, combustion of carbon to give carbon dioxide. C plus O2 giving you CO2. Carbon is the element on the left hand side. CO2 is a compound of carbon in which carbon is very much present and has retained its identity. This happens because in ordinary chemical reactions, we are only manipulating the electrons present outside the nucleus, but we are not touching the protons and neutrons inside the nucleus. And therefore the identity of an element is determined by the number of protons and not by the number of electrons. But in a nuclear reaction, in most cases, the identity of the atom or the element changes. So one element is going to become another element. Second, which I already mentioned, is that only electrons are involved, that to the valence or the outermost electrons in most cases. Whereas here, electrons, extranuclear electrons are not at all involved, only protons and neutrons are involved. The third important factor is this, that you can increase the rate of a chemical reaction by increasing an external factor like temperature. But a nuclear reaction is totally unaffected by an increase in temperature. And the energy that is absorbed or given out is relatively very small and of the order of a few kilojoules. Whereas in nuclear reactions, the amount of energy that is absorbed or given out, particularly when given out, is extremely high. And therefore it is used in the making of nuclear bombs. And the last point, which I have already mentioned, is that in a chemical reaction, the mass of the reactants and the products are equal to one another, and therefore the mass is conserved. But in nuclear reactions, you will have a small mass defect, which means that the mass of the product and the mass of the reactants are not equal, and this difference in mass appears in the form of energy. Scientists have devised a shorthand method of representing the nuclear reactions. Suppose you bombard nitrogen 14 with alpha particle, helium 42, and the product that is formed is oxygen 17 and a proton. This can be represented by the shorthand script N147 alpha P O17 8. So what you do is you first mention the target nucleus, open a parenthesis or a bracket. In that, first put the projectile and then put the emitted particle and then mention the product nuclide. Such reactions are called alpha P reactions. So when you hear something of this sort, when you are surfing the internet, it means that alpha particle is the projectile and a proton is being emitted. Similarly, you can have an alpha N reaction, which means that alpha particle is the projectile and neutron is emitted. You can have a NP reaction where N is the projectile, neutron is the projectile, and proton will be emitted. So we are of course going to take up all these reactions in great detail in the next session. But for the present, let us just remember that we can denote any nuclear reaction in this fashion by mentioning the target nucleus, projectile, emitted particle, and the product. Now, an interesting consequence of nuclear reactions is the discovery, if I can say so, of artificial radioactivity. Now, the transmutation of elements was discovered in 1919 by Rutherford, and then scientists were quite curious to know what happens when lighter nuclei were bombarded with alpha particles. So when, say, a nucleus of boron, B10, is bombarded with alpha particle, what happens? To the surprise of the scientist, in this case Irene Curie, she found out that when boron 10 nucleus is bombarded with alpha particle, it starts emitting not only the expected neutron but also a positron. A positron is the shadow or the antiparticle of the electron having the same mass of the electron but a charge exactly opposite. So the bombardment of a boron nucleus with alpha particle results in the emission of positron, and this continues even after the source of alpha particle is removed. Now this led Irene Curie to come to the conclusion that boron 10 has reacted with the alpha particle to form an unstable nucleus nitrogen 13-7. This unstable N13 nucleus is radioactive. Because it is radioactive, it will undergo disintegration, emitting a positron and giving a stable nucleus of carbon 13-6. Thus, we have started with a stable nucleus. We have converted the stable nucleus into an unstable nucleus and made that unstable nucleus to disintegrate and exhibit radioactivity. This phenomenon is therefore called artificial radioactivity. In the example taken previously, we took nitrogen 14, bombarded nitrogen 14 with a alpha particle, but what we got was oxygen 17, which was stable. In this case, we are taking a stable nucleus, but we are getting an intermediate nucleus which is unstable and undergoes disintegration. So therefore, in summary, when you carry out a nuclear reaction, there are two cases. The product formed can either be stable or it can be unstable. When the product is unstable, it will spontaneously disintegrate, emitting another particle. So therefore, the radioactivity that we are observing in this case is not natural but has been induced, and such radioactivity has been called as induced radioactivity. Let me take one or two other examples. What we are doing here is to take a stable aluminium isotope bombarded with a deuteron to produce aluminium 2813, which is an unstable isotope of aluminium, which spontaneously disintegrates to form silicon 28, which is stable, with the emission of a beta particle. So again, this is an example of artificial or induced radioactivity, where we are converting a stable nucleus to become unstable and then disintegrate. Take the example of sodium 23, which will capture a deuteron, become magnesium with the emission of neutron. Magnesium 24 is unstable, radioactive, and it disintegrates, forming aluminium 2413, which is stable with the emission of a beta particle. In all the three examples that I have quoted, you must note that a stable nucleus is getting converted to an unstable nucleus by an ordinary nuclear reaction, but the product formed being unstable will further disintegrate on its own by emitting some particle like a positron or an electron, and this leads to the phenomenon of artificial radioactivity. Artificial radioactivity has helped us to synthesize many unnatural or man-made elements. I'll quote one example. You can take uranium 238 bombarded with neutron. When you bombard uranium 238 with neutron, it forms uranium 239 with the emission of a gamma radiation. Uranium 239 is unstable. It will disintegrate, showing artificial radioactivity, emitting a beta particle and forming neptunium 239. Please note that since a beta particle is emitted, the mass number will not change, but only the atomic number is increasing by 1 unit. Neptunium 239 is an artificially formed element with a half-life of 23.5. This again is unstable and it disintegrates further spontaneously, forming plutonium 239, which has a half-life of 2.35 days. So thus we have successfully taken a stable nucleus, of course it is radioactive but it is stable, uranium 238, and bombarded with neutron, converted to something unstable, and in turn got two radioactive nuclei, namely neptunium and plutonium. So thus we have synthesized plutonium from uranium-238. And we'll be referring to this reaction again and again when we talk about nuclear fission, because along with uranium-235, plutonium-239 is one such nuclei which can undergo nuclear fission. And therefore many nuclear reactors not only use uranium-235 but they also use plutonium-239, which is obtained from the more abundant uranium-238. I thank you for your patient listening. In this present session, we have covered some of the elementary aspects of what are called nuclear reactions or the artificial transmutation of elements. We have seen how different these reactions are from our regular chemical reactions. We have also seen that energy can either be absorbed or released during these nuclear reactions, but in most cases the energy is absorbed for reasons that I have already mentioned. I have also shown you that during these nuclear reactions, if the product nucleus formed is unstable, it can undergo spontaneous disintegration. Therefore, we have found a method of causing radioactivity artificially, and this phenomenon is therefore called artificial or induced radioactivity. Now, this induced radioactivity has been a great help in synthesizing transuranium elements, or elements which do not occur in nature but which can nevertheless be synthesized by bombarding stable radioactive nuclei like uranium. In the next session, we will take up the nuclear reactions and the types of nuclear reactions involving various projectiles in some detail. We will also be considering nuclear fission and nuclear fusion and doing a quick comparison of the two. Thank you for your patient listening.